Before we begin doing some trigonometric integrals, let's review the different types. So first we have the sine-cosine integrals. Now if one of the exponents is odd, then what one could do is separate one of the, let's say the m is odd, separate one cosine, put it next to the dx, change everything over to sine, and then do this substitution. So I'll do a little example here. Like let's say we have sine 10x cos cubed x dx. Okay, so there we have our odd exponent, and then what we're going to do is put a cosine x next to the dx. And now we'll change cos squared x is 1 minus sine squared x. So we're in the situation where we have all signs here, an expression with only sine 10 times 1 minus sine squared. And if we put u equal to sine x, du is cosine x, and we end up with the integral u to the 10th times 1 minus u squared. So that's what we do if cosine is odd. If sine, the exponent of sine is odd, we can do the same type of thing with sine. We break off one sine, put it next to the dx, and then change the rest over to cosine. And then we're going to do this substitution, u equal cosine and du minus sine x dx. If we have a tangent secant integral, if m is even, the exponent of secant is even, we put secant squared next to the dx and change what remains over to tangent, so everything will be tangent, and we'll have a secant squared next to the dx. And then we do this substitution. Or in this case, again, we have tan secant, but let's say tangent is odd, then what we could do in that case is take one tangent from here and one secant from here and put secant tan next to the dx. That's the derivative of secant. Secant tan next to the dx, change everything over to secant and do this substitution. And finally, if they're both even, sine, cosine both even, we use these identities. So anyway, to reduce the degree. So we go down from a sine squared to cosine to the 1, for example. All right, so anyway, we'll see an example of this in the practice problems. So in number 1, we have cosine x next to the dx, and here we have sines. So we can put, if we put u equal, this is a simple u substitution, if we put u equal to sine x, and then du is right here. So this integral becomes u to the 7th minus u to the 10th du. And we can just use the power rule to solve. And then just substitute back for u, substitute back sine x. In number 2, we have the exponent of sine is odd. So we're going to put one sine next to the dx, pull off one sine. And then we can change sine squared to 1 minus cos squared. So we have all cosines, and then a sine x next to the dx. So that's also good for a u substitution, where u is cosine. And du is minus sine x. Okay, so minus du is sine x dx. So now we're ready to do our substituting. So we have, instead of sine x dx, we have minus du. And here we have cosine to the 10th. That would be u to the 10th, 1 minus u squared. And before we integrate, we have to multiply through. So here we have u to the 10th minus u to the 12th. So that's power rule u to the 11 over 11. Sorry, this is a 12 over here. Minus u to the 13 over 13 plus c. And then just substitute back for u, substitute cosine x. So cosine x instead of u. And number 3, we'll do the same thing. Here we have this odd exponent. And I'm just demonstrating the exponent of sine doesn't have to be an integer. It can be minus 2 to the 5th. Since it's in the denominator, I'm saying minus 2 to the 5th. So we have, we're going to pull off a cosine x. And we're left here with cos squared divided by sine to the 2/5 x. And we're going to change this to 1 minus sine squared. And now we're ready to do our substitution. U equals sine x, and d is cosine x. So there we have 1 minus u squared, u to the 2/5, and here we have du. Let me put my dx in there. All right, now we're going to, before we integrate, we're going to divide term by term. So this is 1 over u to the 2/5 is u to the minus 2/5. And now we have u squared minus u to the 2/5. U squared is u to the 10 over 5. 10 over 5 minus 2 over 5, that's 8 over 5. And we just do a power rule here. U to the minus 2/5 plus 5/5, that's 3/5. Divide by 3/5. U to the 8 over 5 plus 1 plus 5 over 5 is 13 over 5. And divide by 13 over 5. And then just substitute back for u sine x. In number 4, we have a situation for a direct u substitution. If we put u equal to tangent, du is right here. The derivative of tangent is secant squared. So let's do that. So this is just u to the 10th du. Okay, so that's tangent x to the 11th over 11 plus c. And then number 5, we have secant to the 4th. Okay, so that's even. That's one of the situations we look for. And in that case, our plan was to pull off a secant squared and put it next to the dx. So that's the derivative of tangent. So we're going to, if we put u, our plan is to change everything over to tangent, and this will be, and put u equal to tangent x, and this will be the derivative. All right, changing everything to tangent, secant squared is, we have this trigonometric identity, 1 plus tan squared x is equal to secant squared x. Okay, so we're going to just use this. So this is 1 plus tan squared. All right, so now here we have all tan squares, and here we have the derivative of tangent, which is secant. So we're going to put u equal to tan. And here's du. Okay, so we have u to the 10th 1 plus u squared du. And don't forget to multiply through before you integrate. So that's u to the 10th plus u to the 12th. All right, so now integrate u to the 11 over 11 plus u to the 13 over 13 plus c. And substitute back for u, put back tangent x. In number 6, we have the exponent of tangent is odd. So in this case, what we did was we pulled off a secant tan. So let's put that over here. Now, if that's the derivative of secant, so we want u to be secant x. So we want to change everything else over to secant. So what do we have? We pulled off secant tan. That brings us down to secant 6. And this brings us down to tangent squared. Now we want everything here to be secant. So we're going to use the same identity that we had before. Let me put that down again. 1 plus tan squared is secant squared. So secant squared minus 1 is tan squared. All right, so once we do that substitution, we'll be in a good position. All right, so we'll write this as secant 6, secant squared x minus 1, and then we have secant x tangent x. So if we put u equal to secant, we're going to have all u's here, and this will be du. Okay, again, so this integral becomes u to the 6, u squared minus 1, and the rest is du. Multiply through before you do the power rule. So that's u to the 8 minus u to the 6. Okay, now we're ready for the power rule. And now substitute back for u, substitute back secant. This integral is just integral tan squared. We just do that same, use that same trig identity. 1 plus tan squared is equal to secant squared. So this is tan squared is secant squared x minus 1. All right, so this integral becomes the integral of secant squared x minus 1 dx. And since secant squared is the derivative of tangent, we can integrate term by term. We get tangent x, and the integral of 1 is x. When we integrate integrals involving sine and cosine products where both exponents are even, then we use the following identities. Cos squared x is equal to 1 plus cos 2x over 2. And then we have one for sine squared also, but in this case we don't need that one, so we'll go straight to this identity. Let's put the 1/2 on the outside. And so inside we have 1 plus cos 2x. And the integral of 1 is x. Now the integral of cos 2x. Well, this is almost the derivative of sine 2x, except the derivative of sine 2x has a 2 in front. So we're going to put a 1/2 in front since the 2 is missing. So you see how this identity here was helpful in integrating cos squared. Okay, now let's integrate sine to the 4th. So we're going to first of all write this as sine squared x squared. And we're going to use this identity. Sine squared x is equal to 1 minus cos 2x over 2. All right, so let's put that in there. All right, let's square this out. First of all, square the 2 in the denominator, and we can bring out a 1/4. And we're going to square out 1 minus cos 2x times 1 minus cos 2x. All right, so that's 1/4. And here we have 1 times 1. Then we have minus cos 2x minus cos 2x. That's minus 2 cos 2x. And then this times this is plus cos squared 2x dx. And now we're going to integrate term by term. The integral of 1 is x. The integral of cos 2x, okay, the derivative of sine 2x is cos 2x times 2. So this is exactly the derivative of sine 2x. Okay, again, the derivative of sine 2x is cos 2x times 2, and that's what we have over here. Oh, sorry, plus the integral of cos squared 2x dx. Okay, so we're going to have to work on this integral next. And what we're going to do is we're going to use that same trig integral again with a little variation since we have a 2x here instead of an x. So let's write that on the side. So cos squared 2x is equal to 1 plus cosine, and instead of 2x now we're just going to double this and write 4x. 1 plus cos 4x over 2. Alright, so this is what we're going to substitute now, right here, for cos 2x. Let's do this on the side. So on the side we're going to do the integral of cos squared 2x. So it's 1/2 integral 1 plus cos 4x. So we have 1/2 integral of 1 is x. This is the derivative, part of the derivative of sine 4x, the derivative of sine 4x. The derivative of sine 4x is cosine 4x times 4. We're missing the 4, so we have a 1/4 over here. Okay, so this is the integral of cos squared 2x. And we're just going to take that and put it right here. Okay, so finally, as our final answer, we have the following. Let's just take this, and I'm going to continue right here. So we have 1/4 x minus sine 2x plus what we just found here, 1/2 x plus 1/4 sine 4x. And then I'll add on the plus c. So here's the final answer. Okay, so finally we have it. This is the integral of, over here, this is the integral of sine to the 4th. Now, to do a check, one would differentiate this and see if you get sine squared. And it requires a lot of trig substitutions to show that, but this is a lot of trig substitutions, but this is the integral right here. sine to the fourth x dx.